So, thank you very much, Amir, for a wonderful lecture. I just could not take my mind off of what Trump might have said about the transgender shrimp. I don't know. Yeah, you did get funded by the NIH. So, anyway, yeah, it's a challenging world today. So, okay. I think I will try to talk.
Speak
So,
up.
yeah, I will tell you about some examples in my lab. I never had a company. Yeah, so, but still there were collaborations with industry, and I would like to share these things, and then we can talk a little bit more about this. These are, I always like to show the picture. These are the people that do the research in the lab. This is the most important thing. Doesn't matter if it's applied, basic, whatever. These are the people that do the work, and they always deserve the recognition. We were celebrating December 9th, which is a very important day for world football. We can talk about that. Okay, so this is what I will talk to you. First, I will start with the bad example. A collaboration we had with Caesar Stone Company. Then I will talk about 3D printing and a good example, my lab kit. And then what more came out of it. And like what Amir said, how applications then go back. And then a small detour in Hatzelim, which are our neighbors, and something about the whole story. So let's start with Caesar Stone. Maybe some of you have heard about Caesar Stone, in Hebrew, Eben Kesan. Many of you have it in your kitchens, probably. So Caesar Stone is something that looks like marble, but it's not marble. It's actually sand glued with a polymer. And so one of the main problems they have is that you cannot use it outside, because the UV radiation destroys the linkage between the polymer and the sand, and then it starts to break apart. So they came to me, I don't know how, and said, do you have an idea on how to solve this issue, right? And yeah, well, it sounds like an interesting subject, right? How to do, I was then very interested in multivalent bonding. If you have one bond that you have to break, then it's easy. But if you have multiple bonds, even if you break one bond, the two particles will stay together, right? So this was the idea on how to develop something like this. And I had a lot of experience at the time with dendrimer chemistry. Okay? So dendrimers, this is me during my postdoc, I was working with dendrimers. Dendrimers are these fractal molecules that they spread out, fan out, and then you have lots of terminal groups. See, many hands. These are dendrimers. And so my basic idea was, why not use dendrimers to hold on these pieces of sand together, and this will allow us to have Caesar stone outside for many applications. Right? And the idea was good. Then I had one student work on it. We got funding from them just in the beginning of the lab, and it worked perfect. It worked perfect. What was the problem? It's too expensive. So the idea was great. All the thinking behind it was great. It worked. It solved the problem, but it was too expensive, so they never used it. Right? So this is what can happen sometimes, right? At the end of the day, they want to make money. They don't care if the marble is stable outside or not. They want to make more money. So this is a bad example of how they came to us with an idea. I couldn't make it cheaper, right? But I guess you could if you work on it. But I had no interest in working on that. Okay. Now let's go to another example. I've got some molecules here. So we were working on this magnet program, right? This magnet, they bring together industry and research groups under the auspice of the Ministry of Commerce in Israel, and one of the companies, Orbotech, it's a big company, they were interested in developing 3D printing methodologies by stereolithographic methods. So just to tell you more or less how this works, you have this bath, okay, in a layer, and then you irradiate with the UV light that you use to do the 3D printing, you irradiate an image, let's say a circle, okay? And then you lower the bath and another layer comes in, and then you want to make a square up on the circle. Now, if the layer is too thin, your light, your square, will go down to the first layer, right? So you have to make the layers thicker. Okay, if it's too thick, it will not polymerize at the bottom. So you have to like tune the width of the layer. This, of course, hurts the resolution of your 3D printing device. So it's a problem. I said, can you fix this problem? And so we were working on latent olefin metathesis, which is the reaction that we were using to make these very, very tough polymers. And we had an idea that, like a mere switch, we also thought about a switch. Let's make a switch. One switch, you polymerize, but then you turn on another light which kills all of the catalysts. And then you can make the second layer as thin as you want, because there is no catalyst in the second. And again, it worked really nice. And yeah, we published this in a journal that has a name which is good for this conference, right? It's Angewandte Chemie, applied chemistry. So Angewandte Chemie does not publish applied chemistry, it publishes basic science, right? It's one of the most important chemistry journals in the world. But the name is Angewandte Chemie, and this is, I don't know, when, maybe 7 knows when the paper, the journal was founded? Probably the 1800s, right?
Yes.
Yeah, so even then, one of the most influential journals was applied chemistry, right? Angewandte Chemie, even though it's not. Right? Anyways, interesting. So we published this, and it worked really nice. We were able to do this on-off switch. Again, I think because of cost, they didn't use it, but for us it was great because we did a lot of 3D printing from here. From here on, we got into 3D printing, and a lot of basic science came out of this. I think maybe half of my career, a big chunk of my career, and a lot of basic science, like the Journal of the American Society, which is catalysis. Even here is Lemcoff sitting at the back. He was one of the authors in this paper. So a lot of things that came out of 3D printing were because of this. This first forage that we had into 3D printing. We started to think, how can we control it? And so we did a lot of 3D printing, and this, of course, is basic science. Right? This is what we do. Not commercializing of this. I think we have patents, but sometimes the university will write patents just for the sake of it. Not really. I don't know. I guess it depends on how much you want to push it. So also at the time, one of these companies in the consortium was Stratasys. It's a 3D printing company, and they were working on doing polymerization of this molecule without this here. Okay? That's called dicyclopentadiene. It comes from petroleum. It's very, very cheap. When you polymerize it, you get a super tough polymer. It's used for many, many applications. I think it's one of the future materials that we will be using more and more. Very useful, and we were amongst the first that could do 3D printing with it, by our methodology, with our catalysts. So they wanted to work with us, and we did really nice 3D printing with it. There's one problem with this molecule. It smells really bad. It's not toxic, but it smells really bad. Most hydrocarbons with carbon-carbon double bonds smell bad. But this one really smells bad. And one day, one of the people working there in the company, they spilled a little vial into the sink. The sink, there's water. the molecule is very hydrophobic, which means that immediately it wanted to get out of this water. It filled the room with smell. The building was filled with smell. The building was evacuated because of the smell. At that point, they told me, either you remove the smell or we don't work with you anymore. So that's a good incentive, right? So we started to think, we're chemists, what can we do to remove the smell? Okay, let's put a hydroxy group. A hydroxy group has hydrogen bonds. It will make the volatility lower. It will have less smell maybe. But like magic, we cannot explain smell so much. It's very complicated. Maybe one of the most complicated senses that we have. And once we put the hydroxy group there, the smell disappeared. It wasn't, well, yeah, Anna says more or less. She can still smell it. Some people can still smell it. For me, it disappeared. Okay? But not only for the hydroxy, we had this handle now to make a whole new family of polymers. So nobody had ever done this before. So we had this whole new family of polymers that we could do 3D printing with. Here you can see some patent applications that we had in the past. And, oh, sorry. Okay. And what we found out is that we can get polymers with better material properties from this change. It wasn't just removing the smell, it was changing the thermomechanical properties of the material itself. And not only that, when we mixed them together, we even got to these super high glass transition temperatures of 400 Kelvin, unheard of, which is giving you materials that you can even use in space. Right? And now we have a collaboration ongoing to develop these new materials to use in space even, right? Because they're super tough, and it came out because the smell bothered somebody, right? And we would never have gone into trying to make this otherwise. So again, out of a technical issue, problem, came basic research goes back, and you see the back and forth. Okay. Finally, I would like to finish this part with just a very recent collaboration. This was also work by Anna. And I don't know why is he here first? Anna is the first author. I am the last author here in this paper. Anna did all the work. So this is a true collaboration with the company Umicore. Umicore is probably the largest company in the world making catalysts today. Transition metal catalyst, palladium, ruthenium, platinum, rhodium, whatever. Umicore has it. And they were working on these type of catalysts. All of our activation of catalyst was always being done by dissociation of a ruthenium phosphorus bond or a ruthenium sulfur bond. But these have ruthenium carbon bonds. So they're very strong ligands. This makes these catalysts inactive under normal conditions, and you have to activate them. Anna discovered that we can activate them by using UVC light, 254 nanometers UV light, but only if they have this ligand on it. Doesn't matter what it is, and not this one. This is called benzylidine. This is indenylidine. It doesn't matter, but it was a new discovery, right? And again, they are very interested in they sell these catalysts are commercially available, some of them, right? And we discovered how to activate them, and we have an idea why. Better. So this is a true collaboration between industry and basic science, where we put our expertise, they give us the materials together. Okay. I would like to finish with the jojoba story. So very close to us here, Kibbutz Hatzerim has one of the largest jojoba plantations in the world. Okay, Israel is one of the major jojoba producers in the world. Jojoba is a plant that came originally from Arizona in the U.S. Now many people are producing it. Argentina has also very interesting. But in any case, jojoba oil is used for cosmetic purposes, right? So it's very. It came to replace whale oil, so it has advantages. It has properties compared with. So chemically, it looks like this. It's an interesting fatty ester. Usually, fats are triglycerides, right? So you have these are not triglycerides. These are very interesting fats. And when I look at it as a chemist, for me, this molecule was designed to do all of the metathesis, okay? Because of these carbon-carbon bonds here. Right? And this part of the jojoba changes a little bit, right? But the ends are always the same. It's always at the 9th carbon, you have the carbon-carbon double bond. For me, that was amazing. So we said, if we can make very nice things with this jojoba. So I have some friends in Hatzeirim, and we started to collaborate and work on this molecule together. Okay, so 50% of all the jojoba fields in the world are here, right next to us. It's pretty amazing. Yeah, the global, and they're very efficient. So they have 50% of the field, but 30% of the market. Yeah, Israel agriculture is amazing. Here's what they set up this huge plant now in November 2017. So my friends here, and yeah. So if you want, you can go to Hatzeirim and ask them to visit the jojoba plantation. Maybe they'll give you a little gift of the jojoba. Okay, anyways, what do we do with it? So what we did, even back in 2014, you could see, we took the jojoba oil itself, and the idea was we can break these double bonds and join them together, okay? And we can make a very, very long polymer, okay? And extract a C18, which is actually what is used for jet fuel, okay? Not only that, if you get it clean, you could then do other reactions with this and get value-added products. So it was nice, but it was very tough, very hard conditions, as you could see. 200 degrees, high vacuum. This is a nightmare. We had all these kind of side reactions. So it was nice for a very good publication, but that's it, nothing else. But now we found a way, finally, to make it work. And by this new technique that we're doing, soon we're going to publish this, hopefully. It's pretty sure it will work. And now we're making high molecular weight polymers, like these things here, whatever we have, high molecular weight polymers with very pure C18 as the condensate, okay? At very low catalyst loadings, you need very small catalyst, and this is super important. Now, this, if we hydrogenate it, which is really simple, you get like a polyethylene with an ester group every 20 carbons, which will give you very good material properties and also the possibility to degrade it, to hydrolyze it. So we have a polymer that we can hydrolyze. It's going to have much less environmental impact, and all you need is to grow the jojoba, which does not need too much water. About 60% of the seed is oil. So. And I think this is a very practical application of how we were able to think about using olefin metathesis to make a practical application. There's not too much basic science here, right? We didn't develop a new reaction or anything. We just found a way to make this very, very useful. So I think awesome. So we realized the field by producing useful polymer from a biorenewable source. Catalytically, under mild conditions, 100% atom economy. We use every single atom in the jojoba oil. And these are important things that we also have to think about as chemists, right? I mean, our world is not looking so good today. We have many other problems other than chemistry. We have many bigger problems than chemistry in the world, but chemistry and
It's all chemistry.
yeah, it's all chemistry. No, I was thinking more about human conflicts. It's also chemistry at some point. But, in any ways, this is one way to do it. And of course, we say in the next 50 years we won't have oil anymore. It's always, even when I was born, I think they said 50 years have passed. We still have oil, but at some point the oil is going to run out, right? And anyways, we don't know that. But this is an alternative. good alternative, okay, a good way to do it. And I think that the precipitation technique that we developed for this may be used to make other types of polymers. So this is an advancement in basic science as well. So, conclusions. Industry and basic science, often perceived as distinct domains, actually share dynamic and symbiotic relationship that drives technological innovation, scientific understanding, while industry focuses on practical applications. Basic science, of course, this is also written by AI. Yeah, it goes, whatever. Out of the many insights that these AI Claude, I like Claude very much. Better than DeepSeek or ChatGPT. But funding and resource sharing. Okay, basic scientific research often requires significant financial investment. Industry can provide crucial funding and advanced equipment that might be challenging to obtain through traditional academic channels. This is something that it's a double-edged sword, of course. I remember about a decade ago, I went to a tour of universities in England. I was shocked to see that 90% of their funding was in the industry. Completely the opposite of what we have here. Sometimes we have to learn to say, well, thank you to the people of Israel that are funding our research, right? Because, yeah, there it was all industry. And problem solving and innovation, industrial challenges can inspire scientific research questions, as I showed you, I think. Engineering is kind of technical, okay. And a breakthrough in basic science can spark entirely new applications of technologies, like the MRI. I was in the University of Illinois when Paul Lauterbur he received the Nobel Prize for MRI, and he spoke on how it was completely basic research. He had no imagination of what would come out of it, right? And of course, we would not have MRI without his basic research studies. And of course, almost every technological advancement has some basic research before it. So, my conclusion, so long as the researcher remains curiosity-driven, fundamental basic knowledge can be revealed. The technical problem may sometimes be a good starting point to discover something unexpected and new. Okay, these are my conclusions. Just keep being curious, and scientific research, basic research will continue. Thank you.
Yes, Ute.
Yeah, thank you very much. Very illuminating. I wonder, would AI be able to predict the changes of the properties of the molecules by, let's say, adding a hydroxyl group or breaking a double bond or something like that? Would they be able to do that, or do you have to do for chance events and look for chance events and try to change the molecules yourself?
Serendipity versus AI?
Yes.
Yeah, I think AI will be able to do it. Maybe not today, but soon enough. I think it will. Yeah. Yeah, I think we will become obsolete. I don't know, but maybe after I retire. Anyways, I don't know. AI will certainly change the way we do research. Like the internet changed the way we do research. We used to spend hours and hours in the library. More than hours a day. I'm older than most of the people here, but today you want to find something, you just click Google Web of Knowledge, SciFinder, whatever, and you get it. That's it. You don't even have to do research anymore. You just get all the papers. Yeah, I'm sorry, I don't know if that's what you wanted to hear, but that's my opinion. My opinion is that AI will overcome us. Our abilities to think.
I can tell you from the historical point of view, if you don't know the things and you ask AI, you get the absolute wrong answers.
Yeah.
So
AI is learning the mechanisms. So in chemistry, at least, it will know. It will know even if it has never been done before.
The structure of proteins was completely solved essentially by AI.
Yeah.
Huge advance over here.
Yeah, that's what they got the Nobel Prize.
yeah.
Yeah.
Okay, Sebastian Kuschitz.
Kosuch. Every letter in Spanish has one pronunciation.
To practice. Okay, yes.
Okay, first it was a very nice story about serendipity. But my question is about what is basic science. There are people that I won't name that will say that what you are doing is not basic science.
Yeah.
It's applied science. Really applied science for industry or more or less applied science in the academy. But it's still applied science. What do you think about that?
First of all, I agree. There are people that think that. There's a lot of things that I did not show. We are trying to understand why certain wavelengths can activate the catalyst and other wavelengths cannot. Right? Why the benzylidene gets activated and the indolylidene does not. How we change wavelengths. I mean, it's for a purpose, right, to activate the catalyst. But then again, yeah, I'm not studying how two hydrogens meet and make a bond, but even then, I mean, there are very little things in chemistry that you could say that at the end of the day cannot be applied. Right? Most of the things we do, even what you do with quantum tunneling, can be applied at some point.
Hopefully, but no patent.
No, I'm just saying, you're right, that many of the products that we achieve, many of the papers that we publish, can be seen more from a practical point of view. But we do still ask the questions. What makes a catalyst latent? How can we activate it? I think these are fundamental questions that, I mean, of course they have practical applications maybe, but they are fundamental questions. That's how I see it.
More questions?
I'd like to comment that I think AI is basic research. I mean, it's trying to answer the Turing test, which is a philosophical question. And they've been able to do that better and better. But it was always driven by Jeff Hinton, is a neuroscientist. He wanted to understand, maybe get ideas from the brain. Daniel Amit, Polinsky, they're physicists. The fathers of deep learning in Israel, Naftali Tishbi, also a physicist. And it's curiosity driven. And they just got so good and useful that we think of them as not basic science, but it is curiosity driven basic science.
I agree that basic AI is basic science, but was their objective to do applied science in the end with those tools they're doing with basic science or not? Or just
Large language models. It's an amazing insight into basic science.
When you ask,
Amazing insight. The fact that it's so successful is just a fantastic product of that. But it is. It's amazing. The idea of attention is all you need. That's what is called. The paper is called. It's a basic idea. That's attention is all you need.
But it's also learning as it goes.
It's learning, but how it's learning, and what is the fact that you can do a lot of intelligent things just by saying, let's guess what the next word in a sentence is. That's all it does, all these language models. That's an absolutely amazing insight.
when you ask ChatGPT, I did it, will AI change the university research to applied science? They say yes.
That's another basic insight.
It's a very
No,
basic
it
question.
is an empirical insight already, so we
You
don't
should
need
ask
that.
it if it will change it to fundamental basic knowledge, see what it answers.
But I have to answer.
Maybe it will also answer yes.
One last,
And by the way, it acts as academia in the sense that these papers that do these things are not kept as company secrets. They're published on archive.
okay, thank you. I would like to say thank you to Amir and to Gabby for excellent presentations. And And now we have 25 minutes break.